Welcome to our paper presentation. My name is Xiaojiao, I'm a PhD student from Australian Research Centre for Interactive and Virtual Environments in University of South Australia. We present a paper to investigate how to encode data into roughness for physicalizations. In this paper, we focus on investigating how material roughness can be used as a perceptual channel in data physicalization. We describe a method for encoding ordinal data into the perceived roughness of 3D printed surfaces and present an initial exploration of how roughness can be used in multivariate data physicalization. Data physicalization is using physical objects to represent the data, such as using the physical bars to represent the math equations or keyboard frequencies, or using the shapes of the physical objects to represent the populations of the world. But most current physicalizations use visual channels in the physical form, such as color, length, and position. Nowadays, with the commercialized of 3D printer, there is an opportunity to print roughness into a physicalization using readily accessible materials. These 3D print techniques enabled an easier way to control the materials of the physicalization. We could even use 3D printers to print two materials combined and adjust the hardness of certain parts of the objects. Our research pursues the idea of multivariate and multisensory physicalization that uses material-related properties of the physicalization to encode data attributes. Material properties such as roughness and mechanical properties such as hardness can be mapped to the data values. As a step towards an effective multisensory physicalization idea, our work is focused on roughness. To understand how to encode data into roughness, we need to understand how to produce a roughness pattern, how the roughness was perceived, and what could be achieved with this method. There are different ways to control roughness. We categorize these methods into marks and gratings. The marks technique uses patterns of geometric shapes such as cylinders, spheres, cones, and cubes to create rough surfaces. The grating technique uses parallel or crossed bars. We choose dot patterns to create a rough surface, as it is easier to control its parameters to achieve a consistent roughness level on complex non-flat surfaces. The roughness in our paper builds on the work of Blake et al., which explored the perception of roughness through a dot pattern defined by dot diameters, spacing, and dot heights. So in our implementation, the shape of our dots is a truncated cone-based shape with a 60-degree slant angle between the bottom face and the slope face. The dot spacing and dot heights are consistent in our dot pattern, and we only change both top and bottom face dot diameters. The aim of our first user study was to produce a technique for mapping data to the roughness that can be replicated through accessible 3D printing techniques. To achieve the goal, we ran a just noticeable difference experiment. Our sensors, such as touch, have limits on the minimal perceived differences in rough surface. These minimal differences are called just noticeable differences. Understanding these minimal perceivable differences informs how many data classes we can effectively map using a rough surface channel. A common study to determine this JND is the staircase method. The staircase method presents participants a base and a comparison stimulus. In our case, will be the roughness card. Participants respond to whether they perceive a difference in the stimuli with a response of yes or no, or an enforced option of don't know. Based on the participants' answers to whether they detect a difference, we'll step towards the baseline. A non-perceived difference will step away from the baseline. This process continues until a sufficient number of transition points is reached. We use unforced weighted up and down staircase method. This figure is an example of one participant's staircase for one base card, and the final JND is calculated based on the last 4 reversal results. We have 2 conditions in our study, visual tactile and tactile only conditions. We recruited 20 participants aged 22 to 45. According to the calculated average JND, we derived the 7 roughness levels for tactile-only condition and 8 roughness levels for visual tactile condition. The reason we proposed 2 different roughness classes is that we also want to cover the situations where you cannot see the roughness patterns, even potentially for visual impaired people, and also align with our JND conditions. We also ran a second user study to explore what could be achieved with this method. The second user study aimed at understanding the user's impression of multivariate and multisensory physicalization, understanding the effectiveness of roughness as a data encoding approach, and also understanding how users interact with these physicalizations. Based on the proposed roughness levels, we applied the roughness levels proposed based on the tactile-only condition to 5 different physicalization idioms. They are a bar chart, a prism geomap, a prism brain map, a node-link diagram, and an adjacency matrix. To achieve the goal, we ran an observational study using a think aloud protocol, which means the participants will speak out their mind, their actions, and their feelings. We designed the questions such that the participants need to inspect the attributes that are encoded to both the visual channel and roughness channel as shown in the figure. This question required the participants to look for the 3 highest regions and then tactilely compare the roughness on their surface representing minimal wage. We hired 10 participants aged from 22 to 37 for this user study. In our second user study, we found across all idioms, 7 participants answered were correct. Except for the node-link diagram, participants were able to accurately answer questions that involved searching and comparing visual encoded and roughness encoded attributes. Our observations showed a strong tendency among participants to physically engage with the objects. For the composable objects such as bar chart and prism brain map, participants took them apart to inspect the individual marks. We found visual observation was the most common strategy used by participants. Regarding the participants who used haptics to aid in answering the questions, we observed that they interacted with the legend as expected, including using one hand to pick up either an individual mark or the entire physicalization, and using the other hand to touch the legend. Based on this user study, we grouped the participants' feedback into 6 themes. Pragmatic encoding. We noticed that some participants feel the roughness level should associate with the size of the dot, but some participants interpreted the roughness as the density of the data. Affectivity and feelings. We noticed the roughness encoded data invoke variable feelings between participants. In some cases, roughness evokes strong affectivity. Design suggestions. Many participants described combining both roughness and color as an encoding opportunity. The other 3 themes are engagement, use case of roughness, and perceptual challenges. I would like to discuss few takeaways from our paper. The first is about how did the user interpret the data encoded to roughness. In half of the instances, we observed the participants solely inspected the dots on the physicalization surfaces. They often utilized the legend as a visual legend, but in some simple idioms such as bar charts, the legend was only used in the beginning. In another half, participants compared the roughness on the physicalization mark with the legend using two hands. The second point is about what design consideration can we learn for the future. In our user study 1, participants mainly touched the card with their thumb, while in the second study, we observed the participants mainly using their index fingers. In our first study, we found an indication that our participants' index fingers are more sensitive to roughness than their thumbs. From the designer's point of view, strategic placement of rough surfaces and the type of mark geometry that encourages using the index finger might be considered. The third point is about should larger values be encoded to a rougher surface? In artistic physicalization, the use of rough surfaces or sharp edges is subject to the designer's intent. However, we do not know much about the proper mapping direction for roughness encoded data in more pragmatic cases. But in the case of multiple physicalizations, consistency seems to be a more important factor. In conclusion, this paper explores the potential for multivariate data physicalization that makes use of the available bandwidth across both visual and material channels. We concluded with two sets of derived roughness data classifications from our first user study. We gain insights into the interaction between humans and physicalizations, as well as the general theme of qualitative feedback. In the future, we could investigate more physicalization idioms using roughness as an encoding, and other material properties such as shore hardness and different mapping methods such as grading patterns are worth to explore. We could explore more about mapping interval or ratio data into roughness as they are still unknown. Thanks for watching. Please see our paper for more details.